Hello again. So last time we dealt with the section on scalars. We were just dealing with displacement and distance and understanding the difference between displacement and distance. We really looked at one dimension, and now we're going to open this up and we're going to look at two dimensions. So we are going to be talking about vectors. So go ahead and write at the title, at the top of your title, you're dealing with vectors. And you can jot these objectives down, or you can just listen and kind of think like, what is it that I'm supposed to get out of this lecture? We want to be able to state the definition and give examples of vector and scalar variables. So understanding the difference, not only being able to cite that definition, but be able to recognize some examples, give some examples, come up with some, or recognize them from a group of different situations and be able to say oh, that's a scalar, that's a vector. So really being able to apply that definition. Then to analyze and describe position and movement in two dimensions using graphs and Cartesian coordinates. Remember cartography, Cartesian, sounding similar. So we're dealing with that coordinate plane or battleship, for those of you that played, with numbers, not letters. Organize and evaluate position and displacement data into two dimensions. And so it's really a matter of learning how we code in the mathematical world. How do we write these number sentences, these coordinates? Everybody shares the same structure for the way that this information is written, and you need to be very clear on how to go forward with that. All right, so you're going to be answering questions like identify each variable listed below as either a vector or a scalar. You should be able to do this by the end of the lecture. And then being able to solve problems that give you information about something that's in motion, right? A boat travels 5 kilometers east, then 8 kilometers north, then 8 kilometers west. And we're really looking again at displacement. So what are the boat's displacement vectors? Remember, that has to do with direction. What's the final position of the boat? And then what is the distance? That's scalar. What vector will bring the boat back home? So we should be able to apply the information and solve problems like this. So new terms: vector, scalar, magnitude, and coordinates. We're still working within the same equation. X sub f equals x sub I plus d being displacement. So the final position is equal to the initial position plus any displacements. That is our equation. So what is a vector? A vector is some quantity, some length or distance, or you're going to travel this far, but there's a direction attached to it. So some quantities in physics will include directional information. Like you can see, if we're starting at the origin and we're moving in a particular direction, you have the little arrow there, gives us velocity. Velocity is a vector. Force is a vector. There's direction involved in which way you're pushing on something or which direction you're moving. And then our displacement vectors as well, or position, like what's shown here on the graph. So we've got a bunch of different examples. Any variable in which it makes a difference which direction you go, such as forward or backward, that's a vector. So what is a scalar? You've got to know the difference, right? A scalar is other quantities in physics that do not require direction. So mass. Mass is a scalar. There is no direction. Temperature. Temperature is a scalar. There is no direction. Or just the general distance between two objects. That is direction. Now, if you're saying you're going from this object, now you have an origin, and you're going to this one, and now you have a displacement, that is a vector. But if you're just talking about distance between two objects, that's scalar. So on a two-dimensional surface, it does require two values to determine your position. In the last video, we dealt with one dimension. We dealt basically with a number line, and where your position was on that number line really only had to do with one number. When you add the coordinate plane, when you look at x and y, now you have the opportunity within that whole area to determine where on a map, right? Where would you be? A flat map is a two-dimensional surface. It's a really good example of a coordinate plane. So what would you do if you were told to stand 5 kilometers away? What would be your first question? Would you ask, well, away from where? Where should I start? And which direction do you want me to go? Otherwise, you would end up anywhere. You'd be like, I could be anywhere here, right? So we talked about the importance of the origin, right? On a coordinate, every point has an x and a y value, and they're written in the form given here, where you have an open parenthesis x, comma, y, close the parenthesis, where the x and the y would be numbers. So like this point here, given as your example, this guy here is 4, 3. The x and y values are the coordinates of a point, so we call that a point, relative to the origin, which would be 0, 0. So this coordinate is 4, 3, because it is plus 4 along the x-axis and plus 3 along the y-axis. All right, so next up, what is this point? First, we deal with the x, -1, and the y, which is a 3. -1, 3. It is 1 along -1 along the x-axis and plus 3 along the y-axis. So this is how it gets written. Negative numbers tell you which side of the origin the position is located. So if it is to the left or below, it is going to be negative. The position vector is when we connect from the origin to a point. The object is located at this point and it has moved, right, from the origin. And so now we have a arrow that represents a vector, and vector is motion. It is directional, and it is something's moving, and this is the vector. It's direction. What would you do if you were told to walk 5 kilometers? Which direction should I walk? I guess we'll say, starting at the origin, which way should I go? Displacement is a vector since movements need a direction to be fully understood. In investigation 3A, you will add displacement vectors in a plane. And you see these are all of the coordinates. So you add up all these 10 displacements. What 2 perpendicular displacements will move an object from the origin to 4, 3 meters? Can I give you an example? On our first displacement, we're going to put 4. We set that first displacement as 4, 0. You'll see that vector is drawn. And then our second displacement, we'll see, we run the path, and then our second displacement is 0, 3. Because the question asks which 2 perpendicular, so those motions are perpendicular to each other, which 2 perpendicular displacements will move an object from the origin to the position of 4, 3. There it is. Total distance between the start and the finish points is shown here. This is a trick one. This is a 3, 4, 5 right-angled triangle. All right. Answer the questions on your student assignment sheet about this. So you kind of got the example of like how it's going to work, but you're going to need to put your responses onto your investigation and finish that one up. So we talked about this equation earlier today, and then I really wanted to expand it, and I was like, oh. Okay, so we talked about this equation earlier today, and I really wanted to expand it, but I know like some of you I gave the direct instruction. I was like, just separate out the x's, do the x's, and then do the y's separate, and that can help you out. This is the same formula, though you really can run it together. This formula says that the final position is the initial position plus the displacement, but it says it for a coordinate. Okay, now it applies to x and y coordinates separately. So you can add those together, but really like solving the problem is going to happen separately. So you want to kind of pull those all apart. You'll see that the final x coordinate is the initial x coordinate plus the x values of displacement. And then the final y coordinate is the initial y coordinate plus the y values of displacement. So here is a problem as a sample, adding displacement vectors. What is the final position of a robot that starts from the origin, 0, 0 meters, and makes these displacements? So the first one is 5 and 0. The second one, 0 and 3. The third one, -4 and -1. So back to the left 4 and down 1. So that vector is not perpendicular, or doesn't like line up with the axes. You have a diagonal there. And then the final position gives us this total like displacement, right? Displacement, this right here is the displacement of the robot, even though its entire distance is the vectors that it moved along, right? But the final position, 1 over 1 up 2. 1, 2, that's its final position. So there are two ways to add vectors. We can do the graphical addition, and I kind of showed you this, like you use arrows, and you go head to tail, you draw out the arrows. You got 5 on the x, 0, 3 on the second vector, and then -4, -1, and it gives you your final position. And you can actually draw this vector and determine the position. So it's a very hands-on mathematical approach to solving that. But then there's also the numerical addition, which is what we've already kind of like delved into a little bit, where you add the x and the y components separately, and you can get your final position that way. The component method of vector addition is actually the most accurate. This here, let me break it apart. That makes sense. All right. Here's just an interesting thing. This laser cutting machine, and maybe you've dealt with three-dimensional printing, like 3D plastic printing, uses coordinate planes as well. But this laser cutting machine is guided with a set of XY position coordinates that tells exactly where to cut. That is the program. And then this is going to go back to this assessment piece that we started at the beginning of this presentation. I told you you should be able to identify each variable listed below as either a vector or a scalar if there are any variables that are there any variables that are neither vectors nor scalars. So temperature is I gave them all at once. Scalar. Force is a vector. Displacement is a vector. Force has direction. Displacement has direction. Length, just a scalar, because we're not saying which side you need to start from. Velocity is a vector, it has direction, but time is a scalar. We'll figure that one out. All variables used, what? Can't move it. There we go. All variables used in this course are going to be either vectors or scalars. We don't have anything that is neither. All right, so a little bit of practical word problem solving. Please pause and try this one out for yourself. So a boat travels 5 kilometers east, 8 kilometers north, then 8 kilometers west. What are the boat's displacement vectors? What is the final position of the boat? Oh, it's going to give us how to solve this with a couple of different options. This is the vector solving, like was shown here. There we go. Graphical addition using the vector arrows. Sorry. Okay, and there we go. So you can actually see it drawn out. 5, 8, -8. The final position, we would add up those displacements. And they are, you have to add up each set of coordinates. So one thing I want you to notice here, let me get my pen. There we go. These are all of the x's and these are all of the y's. So you can see the y's, you can see the x's. And then you add them up and it gives you the new set of coordinates. There we go. So the next question is, what vector will bring the boat back home? Oh, sorry. So therefore the total distance is 21 kilometers. That's the distance. Where did we go? Sorry about that. Oh, skipped one there. So our total displacements, that gives the final position. And then what distance did the boat travel? The distance is added from each displacement. So therefore just the total distance, 5, 8, 8. You notice that you don't have a negative. So it is absolute value. And absolute value is just like the whole value of that number without direction, without the negative or positive. It doesn't matter, but it's just like they're all positive, if you will. And then what vector will bring the boat back home? The boat's final position is -3, 8 kilometers. To get a 0 requires a displacement of 3 and -8. Okay, I just have a typo here, and I'm going to fix this. So because the boat's final position is -3, and because its final position is -3 and 8, we have to go 3 and -8 in order to get to 0, 0 again. There we go.